Okay, let's get started. And welcome back. This is lecture 5, and we already have this for 1 month. I hope you're doing well, and I guess you're doing well. Maybe you got a little bit frustration last week by the shift details, but as I mentioned, those are it's not mandatory. As long as you understand the concepts and you can use it. And I guess this is basically the goal of this course. And from the tutorial, I got you really read the notebooks and this stuff are easy to use because they're already implemented it in OpenCV. Today, I'm going to move a step forward on image retrieval. The stuff is maybe so far the terms you have heard about or learned about are more about something like the recognition, detection. The why we have to introduce the image retrieval. It's a little bit, it's different from those recognition, detection, tracking stuff. The reason I put here is image retrieval is I will consider it the most straightforward way of using the features. Because last week we have introduced the feature extraction. I think it will be better to introduce how to use the features, right? And image retrieval is the most straightforward way of using the features. Right now, we're using something like the traditional features, like the LBP, like the color histogram, and also the key points. Those are considered conventional features. And in the future, we're going to learn the deep features. Those features extracted by the deep neural networks will be introduced in the future. But the principle of retrieval or the way of using those features are basically very similar to each other. So that's the reason I'm picking it up. And another reason is you're going to learn a lot of concepts or terms in the future when you jump into the deep learning, because deep learning boasts a lot of development in computer vision. A lot of terms have been created recently. So I don't want you to be overwhelmed by those terms. Keep in mind, like most of those tasks or questions in computer vision can be transformed into a retrieval problem or classification problem. And today we're going to introduce the retrieval. And next week, we'll move to the classification. And basically, most of the stuff in the future can be transformed back into these two concepts, either the retrieval or classification. So let's get into it. First of all, like what I have done previously, I would like to show you a demonstration. The demo is about a video. And on the street, you guys are familiar with. This is something taken from the Hong Kong island. And you could see I already modified the tone of that video. Okay, so, okay, that's it. So we're going to use what we're going to introduce today to implement this, meaning that you're able to use some sort of way to modify the video to create such kind of thing. I will explain later. Okay. Oh, this is let me check it out. Okay. Looks good, right? Oh. Okay, and that's it. I basically modify the color tone of different frames, then I put them together to generate a video. However, I'm not going to do it manually. I'm doing it automatically using the technology we're going to introduce today. Okay, here's the outline for this lecture. We're going to introduce the clustering. K means content-based image retrieval and vacuum visual words. And let's see. Okay, so from last week, we start to represent things in the feature space because we have already introduced the simplest way for feature extraction. And after feature extraction, we're actually can represent the content of the image as a number, as numbers, as a sort of numbers, right? And recall where we started. Last time we have some images like that, and we're trying to group them. And conceptually, we figured it out. We can put them into a feature space, and then we can draw some circles to group them. And that's where we started last week. And also we introduced the feature extraction and the way that we'll really have the feature space there, right? We can represent them into numbers and they're really in the feature space. And in the future, we're going to, the way we're using those contents is just about how we play with those numbers. So this actually can be applied to all the stuff we're going to introduce in the future. So I would suggest you, upon have a new task, think them in the feature space. Will help you to build up your conception about the different stuff like the classification, like the retrieval, and so on and so forth. And also, as I put here, in a more general sense, a lot of things we're doing for machine learning it is all about this, how to use the features in the feature space. And I think no matter it's text information, audio information, video information, and other data from the sensors, as long as they can be represented in a feature space, the models or the method we're going to teach in the future can be used. This is not only for images, not only for computer visions. And okay. Anyway, as long as we have numbers in the feature space, the computer can read it. And the next thing is now how computer can draw some circles to group the images, right? So we can answer that question today. Think about that feature space. To draw those circles, you have to make the images inside that circle similar in the same circle, similar to each other, right? The images from different circle should different from each other, right? So that's the idea. So there's two terms you have to keep in mind. Let's see, the circles were, we can call them clusters. A circle is a cluster. And the goal of grouping the pictures using feature using features extracted, we can call it clustering. This is just one of them. We're going to introduce others. Clustering is one. We can group them. Then we're going to introduce the clustering today. And the goal of clustering is to maximize, this is what I have mentioned in different way. Maximize the intercluster, meaning that those between cluster, to maximize the distance between clusters. This is one goal. At the same time, you have to minimize the intracluster. Intracluster meaning that's inside that circle. What inside that circle? We're going to minimize the distances there to put the member images, member vectors with minimum distance to each other. And at the same time, we're trying to increase the distance between clusters that called intercluster. So intercluster, intracluster, two terms you have to keep in mind. They think that space, think that in the feature space, and you will see what we have said. What I have mentioned here is why I can't draw it. Okay, let me switch to somewhere that I can actually use the pen to draw on it, and will be that will be better. It's weird. It happened last time. I can't draw anything on the slides, but I can draw it here. So this is one cluster, and we have to maximize the intercluster, meaning those are intercluster distance. Intercluster distance. We're comparing samples across cluster, and this is another cluster. We have to maximize those distance. At the same time, these are called intra cluster. We have to minimize that part, and that's a goal. Wow. Quite straightforward, right? So in the most popular, one of the most popular method is called k-means. And k-means, as the name indicated, is an algorithm trying to group the samples in the feature space into key clusters or key groups. So the key means key, meaning the number of clusters. Sorry, it's not easy to write using the mouse here. So means, what is means? We're going to introduce it. There are several steps of them. In case you're going to group the features in the feature space into key clusters, you have to, first of all, pick up key centers from the feature space. For example, we have a lot of images represented in the feature space. And we're going to group them into 3 clusters. You have to pick up 3 centers, initial centers to start. You can do that randomly using some kind of randomization method to pick it. And then after that, you can assign each item to its nearest class center, because you have randomly picked the 3. So all the samples in the feature space is going to look for its nearest center there, and they will be assigned to that center. And then you can, after that, this is initial grouping, a clustering, then you will recalculate the mean. The mean means the average or something. I will introduce it later. Let's get an idea first. Then you repeat that process, because you initially pick up 3 initial clusters there. They're not the best. So you have to recalculate the centers for each of the cluster, and then do reassign samples to the centers and repeating that process. Let me explain this in a more straightforward way. For example, there are some samples in the feature space. As I mentioned, it doesn't matter it's images, audios, or tests. As long as you can represent them in the feature space, you can do this. Let's think about that in the feature space. You got some kind of samples there like that. Let's call them samples. And you're going to group them. You're going to generate 3 groups based on their features in the feature space. In that case, you pick up randomly. You can randomly assign 3 of them. Let's call them captain. 3 captains there. So after the assignment, and the other samples is going to report to their nearest captain. So that reportment are indicated by those arrows, like here. They're reporting to this captain, and those are reporting to this one, and those are reporting to this one. But by the appearance, you will see some of them are reporting unreasonable captain, right? By checking out their appearance, like this one, or its appearance are more like are more similar to this group, right? So, but he's reporting to here, so it's unreasonable. But it doesn't matter. This is just an initial grouping, and we can do that again. After those grouping, the initial grouping, we can elect new captain because that one is not that reasonable, right? So it's initially randomly selected, and by the idea of centers, this one will be better centers for that group, right? We can elect him as a captain. So, and well, after repeating that process, this one will be better for the second group. This one probably will be better for the third group, right? So you will see the captainship has been transferred from here to here, this one to this one, and this one to this one by the e-relaxation process, right? Because when you're randomly selecting the captains, you don't have any that information to refer. But after the initial grouping, you already have groups there. So you can recalculate, or you can listen to the soldiers in those groups, right? And let them to elect. It's like they elected a new captain there by themselves. I will introduce, or I will map this idea to the key means later. So just keep in mind, and there are great similarity. So you will see after the re-election, because the captainship has been passed to somebody else for each group. So when we are requiring them to reporting to their captains, and the nearest captains also change because the captains have been changed, right? So in that case, the nearest one you will see here became much more reasonable here when they're reporting to the new captain. And those grouping are basically what we want based on the appearance, right? So, okay, and this is basically the idea of k-means. And let's see how can we apply that for samples to numbers in the feature space? So it's very similar. Let's see, initially we don't know. We got some samples like that. We don't know how to group them. So we can randomly pick up some centers. Let's see. We can pick those 3 as an initial center, and I put K1, K2, K3 there already. And so then after that, we are assigning each of the point to the nearest center. So how can we do that? We can just calculate the distance, right? We can calculate the distance like what we have introduced, like the Euclidean distance, or we can calculate similarity, right? So it's basically very similar. We can pick the nearest one, meaning that's the minimum distance, the one with the minimum distance for each of them. Then we can do the assignment to the nearest one. It's usually taking one, let me take one sample as an example, which is the nearest one to this sample. I may have to calculate the distance to here, and distances to the second one here, and distance to third center here. Then I compare those three distances there and pick up the minimum one. So this is the minimum. Then this sample is assigned to the key 2. So you can repeat that to all those samples in the feature space by comparing their distances to centers. Then you decide which one will be assigned. Okay, this one is easy. Then after that, you will see the grouping, initial grouping has been found. Then you can reassign the captain, and this comes out. This turns out this is actually where we got the name of the means, because key means key. We already know what is a key, and now we're introducing what is the mean. So you will see here we actually calculate some of the new centers like here. So this one has been passed to here. This one moves to here. This one moves to here. So how can we do that? Because this is our initial group, and for each of them, let me put ID for it. This is 1, 2, 3, 4, and so on so forth. They could have an ID there, right? So recall what we have introduced last week. For each of them, we could have this is 1, 2, 3, and so on so forth. Let's see. Those are samples for sample IDs for the members in this group. So this is ID. Then for each of them, no matter which feature extraction method you have used, you're going to have a set of numbers for each of samples, right? Like for the color histogram, you have different dimensions there. And for each of the dimension, you have a numbers there. For example, you have 0.1, 0.8, and so on and so forth for each of them. So you will see this is actually a table and with different fields filtered out. Then to calculate the mean becomes very easy. This is the mean. So let me change it, switch to different color here. So what you have to do is for different dimension, for let's see, this is dimension 1, this is dimension 2. For each of the dimension, we calculate the mean of it, meaning like for the first column, you sum them together and divide it by the number of samples there. You got the mean, right? You actually got the average, right? So you put it here. You have a mean, let's say M1, and you do the same for a second dimension, and you have M2, and you can do it, repeat this for every dimension or every column in this table, and you got a new mean vector right? So you got a mean vector. Mean vector itself, it's a sample of position in the feature space as well. So you can pick up that mean, and this is the K1. This is how K1 has been calculated. And this is also how K2 and K3 have been calculated. They are mean, they are average, they are the centers, mathematical centers of those samples, right? So, and also sometimes people call it gravity of different clusters. So anyway, the idea is very similar and straightforward. Then in that way, you find mean, one mean for each cluster, and putting together you have, because we're doing it for K clusters, you have K means there, right? That's how we got the name, K means. Okay. Is this clear enough? I guess it's straightforward, right? Okay. Any questions? Any questions? Okay. Let's move on. So after the election of new centers, like the election of the captains, we have new centers already. Then we can repeat what we have done previously. The center has been transferred. And we can repeat that assignment by finding out the nearest centers there. So you will see the assignment of some points remain the same, but some of them has already been changed because the center has shifted. Then we have some kind of new grouping like that. So, and after the grouping, the new grouping, we can recalculate the means. Then you're going to have the new centers, right? And then you could do the reassignment, repeating that process. You can repeat that process again and again. Are we going to do it forever? Because no, we're not going to do it forever, right? So it turns out people has already justified. Finally, the means, the centers will be converged to a certain point. So it's ensured the convergency of K-means algorithm has been ensured mathematically. So it's finally will converge to some center, meaning that the center will not move after you regrouping, recalculating. So in that case, you can, after each iteration, when you recalculated the centers, you can compare back to its original center to see how much it has been shifted. Okay? If it's a tiny shift, meaning that it basically doesn't move there, meaning that it has been converged. You can do this by setting a threshold. Right? You can set a really small number there, and as a threshold, if the change less than that threshold, you can stop the iteration. Or practically, actually, people are controlling the number of iterations there. You can say number iteration, because sometimes it's impossible for you to find the theoretic centers there. Well, especially when you have extremely high dimensionality of the feature space. So it takes a lot of efforts for doing that. Okay, so this is K-means, and you see the new center has shifted, and you're going to do that again and again, and when it's until it's converged or it doesn't move. So here are some samples from I am here. You will see that like the images are grouped. Each of the rows here is a cluster. So you will see that has been grouped well. I'm here is a mini project we have done last year for this course. I will introduce it later. We collected some images from there. That's the reason the I'm here appeared in the slides a lot there. I'll introduce it later. So here's another thing quite useful. because actually the dimensionality of the feature space, most of the time, it's really high. It's not easy for us to build in some kind of conceptions on them. So it turns out there's some technology called dimensionality reduction, which will help you to reduce the dimensionality into 2 or 3, because we were able to perceive the dimensionality of 2 and 3. 2 is just a plane, right? And 3, it's just a cubic. So you can we can perceive that. And that's called T. This is a very popular one, TSNE. So we're going to introduce that in the tutorial. And just here, the idea is you can reduce the dimensionality by picking up the most important features of the samples there, by representing them into a 2-dimensional space, like what's shown here. This is the best to view. This is the best, maybe conceptually, the best perspective by looking at the sample in a 2-dimensional space. By the term looking at the samples actually means to visualize the difference of those samples. So this is a best viewpoint to look at the difference of the samples in 2-dimensional space. You can the idea, maybe I can elaborate that a little bit more. Let's see. We have a really high dimensional space. There are many samples there, but there are better perspective. You can look at it all the time, theoretically. For example, let me take more specific samples here. Okay, here are 2 points in the 3D space we are, right? So I got different viewpoint. I can look at those 2 points, right? If I'm looking at here, these 2 are actually overlapped to each other. It's not easy to check out their difference. But if I move a little bit, I see the difference, right? If I move a little bit more, like I'm looking at them at the direction which are actually perpendicular to those 2 connection lines of those 2 ends, it's the best to look at their difference, right? So what I'm doing is actually, because when I'm looking at those samples, I'm indeed mapping those 3-dimensional stuff into 2-dimensional space, because I'm actually view it as an image, right? So this is the way I'm looking at it, and you can use the same stuff, and TSNA is something like that. Will help you to find some viewpoint which you can look at the difference of different samples there in 2-dimensional space, and also you can actually put them into a 3-dimensional space as well. So, but it doesn't mean the original dimensionality of the feature space is 2 or 3. It's just a way to visualize that difference. Okay, and this is a result for those samples, and we have 9 of them. You could see the color of the samples indicates the clustering. So this is one, this is another, and this one is not it's not that good. Those one are not that good in the 2-dimensional space. But keep in mind, when you're thinking about this in the feature space, it doesn't mean that those samples from the same cluster have been separated. It doesn't mean that, because you have only 2-dimensional space. When you're picking up some of the viewpoint for some clusters, maybe it wouldn't be the best viewpoint for other clusters there. You can think about in the way like for those orange samples, for these clusters, they probably have a third dimension. When you're looking at actually from this dimension, so they are projected separately into that 2 dimensions, but they're actually grouped together in the 3rd dimension. Right? If you change your viewpoint, like you change it to here, those samples will be clustered closer to each other, right? So for the red points as well, it happens the very similar way. So anyway, this is just a tools to help you to visualize something, to analyze something. Usually when we got a lot of samples there, it will help us to figure out some kind of trend, general distributions of different groups, right? Okay, this is one. We're going to introduce that later in the tutorial. How to use T, S, and E there. Okay, but from here, you can see clustering is the one of the most, it's a quite straightforward method. K-means is straightforward, and actually it's called unsupervised learning. This is a term. Starting from now, we're going to use the term of learning, because you see machine learning, right? A lot of different types of learning in the future: metric learning and meta learning, and also zero-shot learning. You got a lot of terms of learning, and so starting from now, we're using the term of learning. So this is kind of question.
When you use the word clustering,
yeah,
we saw the K-mean clustering, but there's also different types of clustering.
Yeah, a lot of them. Yeah, like hierarchical clustering. Anyway, there are a lot, like the main shift, a lot of them there now. But the K-means is the most popular and the most straightforward way. So it has been employed a lot. And those clustering, different clustering methods are called unsupervised learning. So let me explain learning first. Learning is a process to help the computer to build up a model about something, usually about something we're trying to understand. Taking an example here, we're trying to understand the grouping of those feature vectors, right? We understand how they can be grouped by investigating how they are naturally similar to each other or different from each other, right? So this algorithm actually learn that aspect automatically using some kind of algorithm. So that's learning. However, during learning, we haven't told the computer which samples should be grouped together, right? We haven't gave that information. But in the future, we're going to give such a kind of information. It is possible. We can tell the computer, oh, you should put these 2 together. You can't put that 2 together, some information like that. But we haven't done it today. So this kind of thing, by giving such kind of information or instructions to the computers, are called supervision. So in the future, we're going to introduce the supervised learning. In that way, we will in the future give the instruction information like that. But today we haven't gave that information. We have done something like there's come out the computers, hey computer, help me to group them, and that's all. I need 3 groups of them, right? So you can give 5 and something like that, but that's the only information you gave to the computers, and the computers will figure it out by themselves automatically. That's unsupervised learning. We haven't supervised that process. That's a name where name comes from. So unsupervised learning. You mean how well or? Oh, yeah. Okay, that's a good question. You're actually talking about how to give the K, right? So the K is kind of application dependent, or it depends on how you're going to, because the unsupervised learning like clustering is some kind of thing will help you to understand the natural distribution of those samples. If in our example, if we know there are three groups of them, we might give that number to them to help us to figure out the grouping by itself. However, we're actually going to introduce another thing, which are quite related. We're going to use a clustering as a method. In some of scenarios, you might try it out. For example, well, you could try 10. See if 10 is a good number to which works the best for your application, because clustering usually will be used as an intermediate step. It's not the final. So anyway, it's just a way to investigate those natural distribution there. We will give more information later, but that's a good question, because there are a lot of other clustering algorithms. They're trying to remove this key. They're trying to give nothing, but they're not actually giving nothing. For another example, there's another group of clustering called density-based clustering, which are group samples based on the density, because the samples we distributed in the feature space in some of the area are very dense to each other, but in other part are sparse to each other. So they're trying to group that based on this density. That's density-based clustering. They use different matrix. Here we're using Euclidean or cosine similarity. There are some density-based matrix there as well. So you could group like that way. But how to determine the K depends on a lot of things, based on what you want, based on what the application wants, or something like that. So it's case by case. We're going to discuss that part later. Okay, so here we have unsupervised learning. I briefly introduced the supervised learning there. We're going to introduce that future. Basically, in machine learning, we have three types of learning. One is unsupervised learning, another is supervised learning, which we have introduced. And here comes the third one, reinforcement learning. Reinforcement learning is something in between those supervised learning and unsupervised learning. I will introduce later. Actually, if you are aware of a recent very popular model called the ChatGPT, right? I guess most people already heard about that. It's using the reinforcement learning to improve its performance. Okay. And in between, they also use some unsupervised learning there as well. Okay, let's just move on. Grouping image is fun, but it's not actually the way we have employed in here. So I would like to clarify a little bit what is here, because I really that name appears a lot in the slides, right? So last year, we have done attendance checking in the classroom, but we're not using the face to the attendance checking. So we have each student pick up one tokens. It could be your water bottle, your laptop, anything else. It's a token for yourself. And every time when you're presented here, we have a link which will help you to take the photo. We have a web app there, which help you take the photo of that token, upload that token to the server. And in the server, we actually will compare the photo you're taking to the one you register. So every student register one token at the beginning of this course. So we'll compare back to that registered token to the one you uploaded. If they are matched, it's saying like you're here. So that's the reason I got a name. I'm here. So taking those as an example, and this is the registered, this might be the registered token for student 1, student 2, student 3, and 4. And those are images they uploaded. If a student 1 uploaded this, and it will be compared back to those registered image to see what is the most similar one. And it turns out it will be this one, which means the identity of that one, the one who uploaded that token is student 1, right? So you can do the same if the student uploaded this one. After comparison, the algorithm will figure out the student 3 is the most possible identity for the uploader, right? So it's actually a process you see here. Every time when you uploaded an image, and it's compared back all the images on file, right? And then you can create something we call the ranked list to put the most similar one at the top and least similar one one by one, following each other. So that's a ranked list. This process is actually called retrieval. That's what we used in here. We actually use the retrieval a lot. Let me take the text retrieval as an example because you're using that every day. In the search engine, you input some of the keywords, and the search engine will figure out and give you a list of articles there or web pages there for you, right? What they have done is similar to this. They're going to extract some feature from the keywords you have inputted, and they will use that feature vector, compare back to the feature vectors of the web pages they have. And they will return that top ranked web pages to you. And image retrieval works in a very similar way. You upload one image, and then you extract the feature vector of this image and compare it back to all the feature vectors in your database. And based on the similarity, you can put a ranked list return to the user. Okay. This is actually called content-based image retrieval. Okay. To clarify a little bit more is even we're called it content-based retrieval, but the term of content doesn't hold that well nowadays, because this term has been generated at a very early age of computer vision. At that time, people thought content is just about the colors, the textures, or local details or something like that. And that has been called content. But it turns out nowadays people are having more expectations on those content. Like we're trying to understand if there is a car there, there is a building there. That's semantic content. So nowadays, it doesn't hold that well, but the content-based image retrieval, the term has been used years ago, long before we have those deep learning and other stuff. So it's still a term used there. But also, you can implement, you can take it in different way by implementing it in different way. For example, if you're going to figure out some kind of features which can represent the semantic content of image, and you can use that feature vector for retrieval. And it will put those content-based retrieval into a higher semantic level beyond those low-level content, right? So anyway, it's image retrieval, and this is the general steps anyway. So first one, extract some feature vector of all images on file, like the registered image in I'm here. And then you extract the feature vector for the query image, like the one you uploaded for attendance checking. And also you compare it to all the images on file. Actually, you compare it, the feature vector, to all the feature vectors on file, right? And you can calculate either the similarity or distances then, and you sort the similarity in a descending order, or you can sort the distance in a ascending order there. Anyway, it generates a ranked list there of the targets. Then you can show that ranked list. Actually, most of the time we're showing the top ranked stuff to the users, right? So this is a general step of image retrieval, and it called CBIR. And you can use, as I mentioned, you can use the cosine similarity, or you can use the Euclidean distance, and maybe you can use other matrix there as well. Okay. Here are some examples from there, and you can see here is a query image. By comparing back to the images on file, those are top ranked image for this one, and this is a second query image, and this is a ranked list for the second image, and for the third as well. You could see basically it worked well for I'm here samples, right? Okay, quite straightforward, right? That's quite straightforward. But however, sometimes we may have a lot of images in the database, right? Like, for example, if we have, like shown here, if we have 1 million targets in the database, it might take 24 hours per query, because you have to compare them back to all the images you have, right? Takes a lot of time. However, you might see it like when you're using the Google search engine, then every time after you issue the queries, and they return the results really fast, right? And they're even proud of by putting how much time has taken for that search there. It's usually milliseconds, right? So, but it turns out if we're going to take 24 hours per query, it's impossible for attendance checking, right? So how can we deal with that problem? Is there a better way? Sure, it will. So this is where we can use the clustering. So, think about that, how we can use the clustering to address that problem. Because clustering is going to help us to group the similar image together.
Instead of looking for the features of every single image, you already cluster them, so you have the features of the cluster, and you just look for the different features of that.
Yeah, that's right. That's the idea. So, because you already grouped them, you can pick up some kind of representative from that feature space to compare, rather than you compare them to all the samples in the feature space, right? Those are some clusters, maybe they have far much larger distance than other clusters there. You can actually escape comparison to this class because they're not supposed to be similar to the query image. Okay? So in that case, you can filter out a lot of clusters at the same time. a huge amount of images to compare. So this is basically how the search engine works. So here, take another three terms there. One is indexing. Indexing is like how you can organize the feature vectors or samples you have in the database into certain structure, which will help you to search, to retrieve the image, a certain kind of, what we're going to use most time is a tree-like stuff. You can organize the samples into a tree-like stuff, so you can search by retrieve this tree structure, rather than you have to compare them back one by one, there, all of them, right? So that's called indexing, putting samples into a certain searching structure. And coarse search is, we're comparing representative rather than we are comparing back to all of them. After comparing back to some representatives, we roughly got some idea where to looking at more, to zoom in, to check out in the feature space. So that's, and we end up with a fine search on the specific location of the feature space, where we might have to compare to every samples in that region. So that's it. So it's 4:30. Let's just take a break for 10 minutes and come back at 4:30. Okay. Okay, let's just continue. Because today we plan to introduce the solution of the challenges of T3. So we might have to hurry up a little bit to leave more time for that part. So here's what I have introduced: the idea of CBIR, a general framework for CBIR, including the actually two parts, indexing and the searching part. And in the searching part, you have the coarse level search and fine level search. The idea is quite straightforward. As Malo has proposed, we can actually use the information of the grouping of the clustering. So here's what we're going to do here. So as I mentioned, indexing is a process by organizing feature vectors in the feature space as a structure. And we're actually trying to generate a tree-like structure like shown here. So what we can do here is, let me pull out the pen. So we can do the clustering for multiple rounds. And here, we might be able to answer the question she proposed, how we can pick up the key, because we don't know how naturally it will be distributed. So let's see, we can conduct the initial clustering on all the samples we have. Then we pick up a number like, because we're actually selecting representatives, right? By clustering, our goal is to selecting some representatives from there. So we can pick up a number like, if we're going to do it, just, we're going to do the coarse retrieval one run. It determines by how many images we can compare at real time, right? For example, if we're going to take 200 milliseconds for every comparison, and we're going to finish that in 1 second, we can only compare to 5 samples there, right? So it determines, but the computer might be much faster, and your computer or server might be much more powerful than the one I mentioned, which takes 200 seconds for every comparison, right? So this depends on the computational power and your expectation about the retrieval. So anyway, you can determine a number here. Let's see. We're able to compare them to 1,000 samples. So in the initial clustering, we can set the key to 1,000, right? Meaning that we're going to have 1,000 cluster after the clustering. And then we can pick the mean from each of the cluster, because that has been calculated in the k-means, right? As a representative. So we're going to, in that case, we're going to put the K1 here and the K2 here, and so on and so forth as the representatives to construct that level, right? And we can either stop here, because in case we don't have too much images, and 1,000 representative is more than enough sometimes, right? So we pick 1,000 representatives. We can stop here, or in case we have a lot, we can do the clustering further, so we can do it in the second round by clustering on the representatives. In that case, in the second round, we have a new K1 prime and the K2 prime, something like that. So we have a new set of representatives. And we can repeat that process again and again until we feel like here is a balance between the efficiency of the search and the effectiveness of the search. So why efficiency right now is easy to understand, right? Because we filtered a lot of comparison. We can just compare them to representatives, right? But what's effectiveness? Will it be affected? Sure. Let me give you information. First of all, let's see that we've already organized the samples as a tree-like structure and see how we can use it. And the search will be something like this. When you have a query, you extract a feature and you compare it to the representative at the top level. Then after that, you might pick up the most similar one, and at the same time, you discard this one, right? By discarding that one, you're actually discard a lot of samples, right? Because it's a hierarchy. And all the samples associated to that sample at the top level, representative at the top level, has been filtered out at the same time. So you repeat that process, you get this level and the level down, and until you reach the roots, you might have to compare all the samples in the roots, right? So, but you could see from here on the path, you compare a limited number of samples. At the same time, you filtered out a lot of other samples. You skipped a lot of samples there, right? So this is easy for you to understand. And this part, as mentioned, has been discarded. And those part has been discarded. And you skipped the comparisons to them. And this is easy for you to understand the efficiency, because it definitely much faster, right? You skip a lot of comparisons there. But will it affect the effectiveness, which means the accuracy of retrieval? Will it be affected by doing this? Yes, right? Why? It's not actually a question. It's straightforward here. We can improve the efficiency, right? Because we have skipped the comparison to a lot of samples there. But the question is, will it affect the accuracy of the retrieval? Meaning that it will affect you, will it happen like sometime the one you're looking for is in the database, but it will be ignored by these types of searching process? Will it be ignored? Is it possible? Yeah. Yeah, that's right. So because the clustering sometimes has no guidance from the human being. It's the grouping is actually depending on what kind of features they're using, right? The feature can represent the content better or worse based on which features you are using, right? If you're picking up not so good features and the grouping doesn't that well to match your demand, right? This is one. Another thing is in most of the algorithms, actually we are assigning one sample to one cluster, meaning that it's determinative there. The membership of samples to cluster has been already hard-coded there. So, meaning sometimes at the boundary of clusters, samples are actually quite similar to each other sometimes. they might be what the users want. But by doing this, the neighboring cluster might be ignored, which prevents you to find those surrounding neighborhood samples around the query samples, right? So it could happen like that way. Let me give you, like I mentioned, we got to think about that in the feature space. Let's take that into a feature space perspective. What we're doing here is like, we come out some initial grouping. Let me change it into different color. What for better demonstrating what we have done here. So let's see. Initially, we have those 3 clusters. This might corresponding to the first round clustering, the results, right? Then you do it further. What we're going to have will be something like, so we further divided that feature space, something like that, something like that. And, oh, sorry, it's not like that way. This is another way. You can do that as well. That's called top down. And what we are actually doing is, but taking this chance to let you know, we can construct that way, either bottom up, and we can do it top down as well. Right? We can divide each of the cluster as well. So what have drawn here, it's different from what I have introduced. This is a top down method. We can do it bottom up. I have introduced the bottom up way. So let's put the bottom up here. But either way, it's either way, it's the same. The idea is the same. So what we have done is bottom up. Let's see. In bottom up, we initially have a lot of samples there. And we have much smaller clustering, a smaller cluster there. So initially, we're having something like that. Each of the circles corresponding to this one, the result of the first clustering. And let's go up, because we're going to pick up each of the representatives from the center, right? This is what happened in the feature space. So we're going to do that clustering on those representatives again. So it's going to give us something like, as shown here. We are actually kind of merging them. So this corresponding to this part, each of that cluster. And we can repeat that process again, which will further merge them like this. This is bottom up way, like what we have introduced, right? But either way, you're going to have the problem, like, because you're doing it top down. I mean, the searching process is top down. So every time you located one cluster, for example, this is the one you located at the first round, like shown here. but there are some samples in case the query is here. There might be some samples are very similar to that query image, but are located in other clusters you ignored, right? You discard it. So it will happen sometime. So in that case, it will affect your accuracy of that retrieval. But how to avoid or how to address that problem? Is there a way we can address it? Yes, we can. It's always we have to. It happens a lot in computer science, and if you want to improve the performance of one side, you might have to pay at the price of the other side, right? So if we want to improve the accuracy, we might have to sacrifice the efficiency, right? So what we can do here is every time after comparison, rather than just pick up the most similar one, we can pick 3 or 5, right? In that case, we still filtered out of other clusters, which might be irrelevant, but at the same time, we are taking more samples to compare, and which increase the probability for us to locate some of samples across cluster, right? But at the same time, it increases the time of comparison. It sacrifices the efficiency. Right? So you have to take a balance when building up applications there. Okay, that has been actually researched a lot. What is the best structure? What is the best tree structure for retrieval? What is the best strategy by filtering out or by picking up the most similar representatives there? So I guess nowadays you can just use it because people has already built it up. And this is general framework of CBIR. You can see here, it's include the indexing. This is one for indexing, which can be done offline. You got a lot of images there, you extract the feature, put them into a database, and also you can generate a tree structure for indexing. And once you have a query image, you extract the feature, and using the indexing structure to do the comparison, similarity will be measured. Then you have a ranked list, top ranked images provided to the user. Okay. Yeah, that's it. Okay. So here, everything works well, but here's one thing. What we have introduced here is with the assumption like there's only one feature for an image, right? But actually we have introduced, you might have multiple feature vectors for one image, especially for the local features like the key points stuff we introduced last week, right? In that case, when you're going to conduct a comparison, it's such a headache, right? Because you can't use your matcher. We have introduced the matcher, right? You can do the point-to-point matching, which will give you an accurate evaluation about the similarity between features based on their details, right? You can do that, but it takes a lot of time. If you really try the notebook, you will understand it takes a lot of efforts there, right? It takes a lot of time to extract the feature because the local feature is expensive to extract, and comparison, it's even costly than the extraction, right? Because you're going to have a lot of points there. So how we can address that problem? Then the idea is called bag of words. We can use a bag of words by summarize those details into a general description about the local details. And That's called visual words. Because the reason we have backwards and back visual words is the idea originally invented from the text domain. It's called backwards. Looking at this, the idea is you can consider, let me introduce backwards first. In the text domain, every article can be considered as a bag. And in each bag, there are some words there, a lot of words there. Then you can calculate a statistics for that bag, like what I have used. You can calculate frequency for each of the words, right? And you can create a histogram over the words. Actually, what they are doing is not actually using all the words. They will generate a vocabulary. Only a certain words, only certain words will be selected as a vocabulary words, or keywords, or code book, or something like that. And they will calculate the histogram based on that vocabulary and for each of the article. So this is backwards. And very similarly, we can consider every image as a bag. And there are some local details can be considered as the visual words. So by borrowing the idea from text domain, we can have the bag of visual words in that case. But how we can do that? Because this is when you're trying to do it on images, it's not that straightforward, because words are just word, text domain. You type that words, as long as you know the characters of the words, and you know the words, that's determinative, right? It's determined by the characters. However, visual words is different, because you're going to be affected by a lot of stuff like illumination, the viewpoints, the scale, like we have introduced last week, right? So even one specific detail, it will be represented in different way, meaning that you have different sets of numbers there for the same detail. So it's kind of challenging there. But the idea is straightforward. For each of the image, you can decompose them into a set of local detail features. Then you can calculate the histogram. Like we have a vocabulary here as well. You see, those are local details as a vocabulary. You will see here, this set of details are the same when you're calculating the histogram. And you see, these words has been decomposed to here, and you calculate that histogram. The idea is straightforward, right? So we can do that by using the local feature extractor, like the SIFT we have introduced last week, right? So the idea is for each of that image, you can extract some of the local key points there, and you can put them, you can pull them here together. And this pool consists of key points from different images. For example, this is image 1, image 2, image 3, and you can put them all together as a pool there. Then in that case, you can use the clustering. Here we're using the clustering again to generate a code book, because we're not going to use all the local points, right? Because there are a lot you could see from that image. One image contains a lot of key points there. We have to pick up the most representative words in that case. So here the clustering comes to play again. Clustering can help us to select the representative key points there. After pulling pulling all the key points together, we can run clustering. In that case, we can pick up the clustering. It's also depend on what I have introduced, depend on what kind of efficiency you're looking for, what kind of accuracy you're looking for. You have to take a balance between those two, and takes a lot of efforts to try and error to figure that out sometime. So anyway, you can use clustering, and you can pick up one most representative words from each of the cluster, like the C1, C2, and C3 here. And then you have a code book there, C1, C2, C3, and others. So those keywords are representative. Most representative one, we can use this as a vocabulary. And
I'm not sure how I understand how we can cluster the descriptors, because if I remember correctly, the descriptors were a location on an image with an orientation, right?
Yeah.
So how can I find the mean for all these different points, like to find like a representative?
Yeah.
For a particular.
Okay, good question. So local features like in the SIF, actually we have two parts. One is detection, another is description, right? Detection is to find the location and orientation of that point. Description is trying to represent the local details, right? In the detection, you have the orientation stuff and location stuff you mentioned, but when you're using that as a representative, those two doesn't matter that much, because in the future, you're going to look at it in different scale and different orientations there. So those two doesn't matter. What matters is the description, the last part, which we rotate that key point to the upright orientation, right? You remember? Then we extract the gradients from there as a description. That description is a feature vector. We're using 128. So for each of that point is a vector of dimensionality of 128. In that case, you have a feature space of 128 there, which you can put all the key points into that space. Then you can conduct the clustering. That's what we're doing here. So, answer your question? Okay. So, but it's good question. Taking that chance to clarify what we have introduced there. In that case, we have a code book. This code book consists of representative key points there, and we call them visual words there. Those can be considered like the actual words, actual visual words, like the text words, right? The others hasn't been selected. You can consider them as a variant of those visual words, because it's also for every such kind of key points, it's a little it is generated with a little bit shift to that representative, right? So we can consider them as variants. After that, you have a code book. Then for each of the image, you still have a set of key points. And it turns out that you have to calculate the histogram. And you can do that like for each of the words in the image. I mean, for each of the key points in the image, you can compare its descriptor, the feature vector, to every representative there. And you can pick up the most similar one and assign that words to that code. In that case, you can generate a histogram. Like those are vocabulary representatives, and here's an image. And we may have a lot of key points there. Let's see, we have K1, K2, K3. Then we can actually compare this to all of them, and maybe we figure out this is C1 is the most similar one to K1, right? So we put the K1 into the bin of C1, and we repeat that for key 2. Maybe key 2 will be assigned to key 3, and so on and so forth. You might have the key I here, key J here. So in that, at the end, you're able to count the number of words which has been assigned to each of the code or visual words in the vocabulary, right? For that, you generate a histogram. Like we have done this a lot for the colors, for textures as well, right? So this is ideal histogram. Is this clear? Okay, clear enough, right? But however, it turns out this kind of assignment is assigning one key point to one visual words there. There are other assignments methods. Like you can, rather than just assign them to the bin, you can use the similarity, because for example, K1 has a similarity to key 1 has a similarity, can be calculated in between the K1 and the C1. Instead of putting that words into bin, we can put this similarity into that bin instead of put the words there, because that is kind of amount indicating the membership of K1 to C1. And you can do that the same for C2 and C3 there as well. That's called a soft weighting assignment. So you can accumulate the membership indicator to generate a histogram as well. This doesn't assign one key point to a specific visual words. Rather, it's assigned using the similarity as an indicator. So this is another one. And also you can sometimes you can pick up the top 3 visual words to do the assignments rather than assign them to all of them. So that can filter a lot of noises there. So anyway, there are different ways of assignment. People have done a lot of research on that as well. So I will skip that part just to provide some framework for you in case you're going to read that paper in the future. So anyway, after that, we can calculate the histogram for each of the image. Here you could see we got one feature vector for one image again, for every image again, right? So we can repeat either the clustering and retrieval on this image. And that goes back to the same framework we have introduced. Okay, and here's the result. And you will see here, the first column is the query. And by using bag of words, you could see basically it works very well, right? So sometimes not. And there's another example there. Okay, that's the CBIR. We have to hurry a little bit. So in addition to CBIR, and we actually got a lot of solutions in between, like in, what has been used in YouTube, it's mostly based on text information. They are doing text retrieval because there is one caption and text associated to each of the video. When you're searching, they're actually based on your query words, the similarity of the query words and those captions and text there. So they're basically using the text information. That works well sometimes, but in case we have much more expectations on those kind of stuff, and people are looking for better method. And okay, And as I mentioned, content-based retrieval most of the time are referring to the low-level features, because the term has been used very early, very early age of computer vision. So, but content itself, it doesn't mean that way. So here's semantic-based retrieval as well, trying to mine the high-level features like what I mentioned, the cars and buildings, persons from there. So you can build that up with the technology we're going to introduce in the future. We will get back to there later. Okay, we still have some time, and I'm actually showing a new toy at the very beginning. Let me explain what it is. This is actually the original video. This is the original video. So you could see here, this is a street you might be familiar with at the Hong Kong Island. So this is the whole video. What I have done there is I'm trying to verify is the vector words good enough to help us to find the near duplicate keyframes, meaning that if that works well to create a feature vector, and the neighboring frames should be similar to each other, right? Because the neighboring frames are containing very similar content when you're taking that video from the bus, right? It's going to include the similar buildings and similar signs and other stuff there, right? So if we're going, the way we're verifying that is I pick up some keyframes from this video. Actually, I take one from every 20 frames there. So what's shown here, those are considered keyframes. So then I'm going to use the backwards to extract one feature vector for each of the frames. And first of all, I extract the feature vector for keyframes there. Then I will compare every intermediate frame, the backwards feature, to all the keyframes. For example, I pick up one frame from here. Let's say it's F1. It's in between the keyframe 0 and the keyframe 20. So its content should, let me change to another color. The content should be very similar to the keyframe 0 and the keyframe 20, right? Because it's in between these keyframes. And by checking out the time point, you can actually find if it's closer to 0, the similar will be closer to 0. Otherwise, it will be more similar to the 20, right? So by using the backwards, we can actually compare this to all those keyframes. In that case, we're going to have a ranked list of keyframes as a result for F1, right? So in the best cases, it might be returned as something like the, let's see, key 0, key 20, because those are the most similar keyframes so far, right? So so this is a way I'm checking out. If we can repeat that process to all the intermediate frames to find the nearest, the most similar keyframes there, it works well. We should be able to, that means the backwards works very well if it's located the right neighboring keyframes all the time, right? So, but it's not easy to check it out because to visualize it. So what you have seen is actually a way to visualize it And also, I think it's more fancy way to visualize it. What I have done here is I assign a tone, a color tone to each of the keyframe, like you see here. Different keyframes, they have different color, right? So for every intermediate frame, like F1 again, I will pick up the color tone of the two top rank keyframes to combine its own color. For example, in the best cases, the keyframe 0 and the keyframe 20 is the best match for these two. Then I will combine the tone of the tones of those two keyframes that generates a color tone of F1. So I will visualize this F1 here using the generated tone. It works well because in case K0 and K20 has been located successfully, you are able to visualize a smooth change of tone from the 0 to 20, right? If it works well. But if in case it doesn't work well, what will happen? In case it's located these two keyframes, and key1 will be generated with a tone as a combined tones of these two frames, right? But these two frames have a very different tone, color tone from the right position to the right position, right? In case it doesn't work very well, it's well showing a blinking or something of color tone there, right? So what we have seen at the very beginning actually is a bad case. It doesn't match very well. So you see a lot of blinking there, even it's fancy, right? So let me put out that this is the idea to do it. So even this video looks fancy, but it's blinking. Okay? So you're not supposed to see that blinking. Everything should be changed smoothly there. Even it's fancy, but it doesn't make any sense for that similarity comparison. So this is a bad case, but the effect itself looks fancy. So what we are looking for right now, as I mentioned, you can combine the tones of the keyframe is located. What you're supposed to see if everything works well, it will be something like that. The tones change gradually, like this, right? So this one worked very well. So. Okay, so okay, that's it. So this is a way to visualize how it works. And I guess something you need is here, because what you need is the key point extraction we have introduced already. And also backwards, we're going to learn in the tutorial. We provide the codes. But you need one thing to change the tone of image. It's what's shown here. Actually, there is another space called HSV space, because we're using RGB most of the time. RGB is indication of the components, color components or color channel for each pixel. That's we introduced so far. But in addition to that, there is HSV. HSV is another space which will tells you for each pixel the hue component. That means the color, the tone. Sometimes we use that term, the tone. And S is the saturation of that color, how saturated it is. And V is the intensity of that pixel. So in case we want to change the tone, we can modify the edge components, which is the hue, right? So this is what I have done here. For a frame represented as RGB, I'm converting it to a HSV space, like shown here, because in OpenCV it's BGR. So I convert that HSV, and I split the channels of HSV into 3 channels, so I can modify each of them. And here I actually cancel the original hue by multiplying by 0, because 0 goes to 0, and the hue component is in the range of 0 to 120, 180. So I add a little bit shift there to the hue, because different the hue of keyframe can be controlled by a number. So I can to find the combination of the tones of 2 keyframes, I can just take the average or something like that, weighted average of their hue numbers there. So I will put that as a shift parameter to pass into this function, and it will modify the frames that way. So modify the hue, and then I will combine them back to the H and SV there as a new image, and return it back to compose them into the BGR space, converting that way, and return them. So this is a function you might need for doing that. And in addition, I've already uploaded the original video into Blackboard, and you can try it out. Take that as a challenge there, and we will release the sample code later. Okay, so in fact, you're going to have all the code in this course. So as I mentioned, I'm going to share a quick sharing what we have in the challenge in the tutorial 3. Let me check it out. Where is it? Okay, this one. So in the T3, we have challenges modifying those image. So I guess most people have already figured it out. This image is kindly blurred, right? So we're going to extract the edge. We can, because we want enhance the edge, make it sharper. That's called a sharpening process. So we can use the edge detector, find the edges of this image, and we can use that edge information to enhance the original image by multiplying the edge value to the original image. This is actually what we have done here. And by doing that, because the one with the edges will have larger values, and then the other pixels doesn't have an edge there. So by doing the multiplication, those edge pixel in the original image will end up with larger values and other pixels without edges, right? So this is the enhancement we have done, actually. So after that, you will see something like this. The edge, if you compare back, this blurred image, the edges has been enhanced here, right? So that's what happened. But at the same time, because this process is changing the range, the value range, because you have multiplied something, and which will actually finally make it look darker than the original image. So in that case, we have to rescale the range to make it brighter. So that's what we have done as a second step, and that's the final result. If you compare back those edge enhanced stuff, it's become brighter, and it with a better contrast as well. So, and the code is here. I'm going to upload this code to Blackboard. So you can check it out by yourself. And first of all, enhance the edges, then brighten the images there. 2 steps there. And first step is taken by multiplication. Second way, it's also a weighted multiplication by changing the range. Okay, this is one. The second challenge is here is I see a lot of students have already tried it out. It's such a headache, right? However, the idea to address this problem is very simple. The one we can't find the body of viruses is, well, no matter what kind of SE, the structure elements you're using, you can't actually find a good fit to there, right? I guess some students already tried a lot of SEs there in between. Right? But the problem is our target virus actually is a round objects. It's like a circle, appears as a circle in that picture. In that case, it's not easy for you to define a well rectangle SE to match that round objects. So the idea is very simple. We can make a round SE rather than a squared SE there. So what we have done is modify this SE as a round, as a circle. In case you should define some kind of thing, some kind of circle which are larger than this part. So this part will be filtered out. But at the same time, it's smaller than this body part in a way that this part will be preserved, right? In case it's fit into this body. And at the same time, it's filtered out these interactions as well. So this is basically what we have done. So checking it out here. Here's the result. Here's the SE we have defined. You could see we actually put it 0 for those at the corner, at the corners, right? So, and which will give you some result like this. Oh, you can see this will happens when you go. The circle goes to here, and this might be the actual body of that viruses there. And then you can just count those to know how many viruses there. So that's very easy. And this is for putting back those results to the original images. And you could see those parts actually locate each of the virus very well. No. Okay, that's the idea. So I'm going to upload this code to the Blackboard so you can check it out by yourself. This is for T3. And this is end of lecture 5. And any questions? You can take some questions there. Okay, if you don't have the question, and that's the end of lecture 5. Thank you guys for coming. See you next week. Bye-bye. Okay.